Hello everyone. So in this talk, we are going to talk about Gluing Karcher Scherk saddle towers. The content of this talk is from an ongoing series of papers. The first of the series was a joint work with Martin Trecet from Tours and was put on archive several months ago. As for the second paper of the series, I just finished writing and it will be on archive very soon. This is actually one of the reasons that the talk was not uploaded earlier, for which I apologize to the organizer. We are instructed to divide the talk into short videos. So the talk will be organized into four parts. In the first part, I will introduce the background to motivate the glue construction. The second part is a sketch of our glue construction, and in the third part I will give the necessary conditions for the construction to succeed. This is actually our main results. In last part, I will give a lot of examples that can be obtained from our construction. So, why do we want to glue saddle towers? Well, people might have different motivation. So I don't know about my co-author Martin, although I do have a rough idea about his motivation, but my motivation is quite clear. I'm interested in the moduli space of triply periodic minimal surfaces of genus 3. So in this part, I'm introduced this background. So a TPMS means a triply periodic minimal surface, which is a minimal surface that is periodic in three linearly independent directions. Another way to put it, it is a minimal surface in the flat 2 torus. I always say that this is a fantastic geometric object that combines two of the most beautiful things, the bubbles film that is minimal and the crystal that is periodic. An important remark here is that in the neighborhood of a generic TPMS, there is a 5-parameter deformation family up to scalings and Euclidean motions. This is actually in correspondence with the deformation of the three-dimensional lattice. So a generic TPMS deforms with its lattice. But we will see that the moduli space of TPMS has singular points. So there are occasionally TPMSs that may deform in different ways as its lattice. The minimum genus of a TPMS is 3. This was proved by Meeks in his thesis in 1975, but I believe people knew this even earlier. So those TPMSs of genus 3 will be abbreviated as TPMS G3. Meeks also proved that each TPMS G3 has 8 points where the Gauss curvature vanishes. These are called flat points. And the inversions in these 8 points are symmetries of the surface. Moreover, up to translations, the 8 points are actually the 8 half-lattice points. That is, they are either at the lattice point or at the edge centers, face centers, or body centers. The history of TPMS traces back to Schwarz, who participated in a contest that asks to use elliptic functions to solve interesting problems. So Schwarz wrote a paper in which he constructed 5 new TPMSs and won the prize of the competition. Now we call them Schwarz P, D, CLP, and H surfaces. Unknown to many, Schwarz was also aware of many tetragonal and rhombohedral deformation families. The picture here shows the P surface. We can see that the surface is very symmetric. Indeed, it contains a lot of straight asymptotic lines and many planar curvature lines. Around each straight asymptotic line, you have a rotation symmetry of order 2, and across each planar curvature line, you have a reflection symmetry. So what Schwarz did is just to construct a small piece of this surface which can be extended by rotations and reflections. Eventually, it becomes a TPMS spanning the whole space. Note that all Schwarz surfaces are of genus 3, the most smallest possible genus. Later, a student of Schwarz constructed a TPMS of genus 9, but the next TPMS of genus 3 had to wait for more than a century until 1970. Hao Chen, then a scientist at NASA, revived Schwarz's method and discovered a dozen of new TPMSs. Most of his surfaces, like Schwarz's surfaces, are very symmetric, admitting many straight lines and reflection planes. But all of them have higher genus, with one exception. He did discover a new TPMS of genus 3, which he called the gyroid. Gyroid is very special in that it does not have any straight line nor planar curvature line, which is very remarkable. So the rigorous proof of gyroid is not easy. Most of Chen's surfaces were later proved by Karcher using the so-called conjugate Plateau method, but it did not work for gyroid for the lack of straight lines and reflection planes. It was until 1996 that Grosse Baumann and Wolgemuth, they are students of Karcher, I believe, they managed to rigorously prove the existence of gyroid. Around the same time, in 1975, Meeks, a mathematician, studied TPMSs in his thesis. We have already seen some of his results. Another remarkable result of him is that he proved the existence of a 5-parameter family of TPMSs of genus 3. Surfaces in this family can be characterized by an orientation reversing translational symmetry. Recall that a generic TPMS has locally a 5-parameter deformation family, so Meeks family is the best that one could expect. Most remarkably, Meeks family contains all the TPMS G3s known at the time, with two exceptions. One is Schwarz's H surface and the other is Chen's gyroid. So again in the 1970s, a paper in Nature pointed out that TPMS can be used to model the so-called bicontinuous structure. This is something that physicists, chemists, biologists, and material scientists are very interested in. Afterwards, TPMSs became a very hot topic in nature science. They have been observed in the wings of butterflies, in the cells, and in neutral stars, literally everywhere. Then, in 1990s, physicists began to contribute in the mathematics of TPMSs, and their results are really remarkable. So the scientists on this slide, they have, for instance, discovered the tetragonal and the rhombohedral deformations of the gyroid. Mathematicians, on the other hand, falls far behind. So these deformations of the gyroid were proved only very recently by me. Interestingly, as gyroid does not lie in Meeks family, neither do their deformations, but both deformation family um, join Meeks family at one end. So you can see that the um, TG, which means tetragonal gyroid, joins Schwarz TD family here. TD means tetragonal deformation of diamond. And here the RG, which is the rhombohedral deformation of gyroid, joins the RPD, which is the rhombohedral deformation of P and D surfaces at this point. So later we will see that the other ends of the families are saddle towers. This is actually a main motivation of our project. So the next TPMS of genus 3 had to wait for another 2 decades until very recently. Matthias Weber and me discovered 2 new orthorhombic deformation families, one for Schwarz D and the other for Schwarz H, both described by 2 parameters. Remarkably, our new surfaces do not lie in Meeks family, but intersect the Meeks family in a 1-parameter family. This is most surprising for the deformation from Schwarz-D because this must be different from the previously known classical deformation, which is in mixed family. So we named it Odelta. An important consequence of our discovery is that all known TPMs are now connected. They can all deform from one to another along a path within the space of TPMs G3s. Let us pause for a moment and think about the TPMs G3s that we have seen so far. The history feels like playing a jigsaw puzzle. You know, one strategy to play the jigsaw puzzle is to find a special piece and expand from there. In our case, the special pieces are found by Schwarz and Schoen's, and all other discoveries are expanding their discovery. But another strategy is to play jigsaw puzzle is to starting from boundary pieces. This is what Martin Trecet, my co-author, has started to do in 2002. He developed the node opening technique to construct minimal surfaces that looks like horizontal planes connected by catenoid necks. He used this method to construct TPMs in 2008, and recently we collaborated in another project where we obtained a complete description for TPMs of Gen 3. So in this construction, we are not only interested in the fact that TPMs may converge to catenoids, but we are also interested in the positions of the catenoids. In fact, the positions are governed by a so-called balance condition. This could be described as follows. So there is an interaction between the catenoid necks, like those between electric charges. Necks in the same layer attract, necks in the adjacent layers repulse, and the interaction between necks further away is ignored. Quantitatively, the interactions are similar to electrostatic force in the two-dimensional universe, so the potential is logarithmic to the distance. Here I say that the balance is like Cheerios, because you can see similar phenomena in the mornings when you put Cheerios in the milk. Every piece of Cheerio will raise the surface of milk, and the capillary force will lead them to approach each other. The same is true if you put two oil drops in the milk, because they both lower the surface, and the capillary force will lead them to attract. But a Cheerio piece and an oil drop will repulse each other. This is the same interaction as you see here for the catenoid necks. So, in the spirit of Martin, a nature question is, what are the possible limits of TPM's G3s? If you look at the limits of Weierstrass data, you will see possible limits are shown as shown here. The catenoids, helicoids, singly periodic Riemann examples, Karcher Scherk saddle towers, and doubly periodic KMR examples. I conjecture that these are all possible limits. So assume that this conjecture is true. Then a next step is to study each of these limits. Recall that when we say catenoid limit, for instance, we also want to describe how the catenoids are glued together to form the TPMs. The components to glue, here catenoid, and the glue pattern, these two information together give us a complete picture, and we expect that this picture is generically described by 5 parameters, which is expected. So what is the state of art? How much do we know about the limits of TPMs G3s? Well, Trecet and me have studied catenoid limits. We have a complete description, as we mentioned, which is a simple formula for whose solutions give the positions of the catenoids. But this is not enough because we still don't have a clear idea about the solution space. Actually, to study the solution space seems very difficult. On the other hand, I believe that the helicoid limits, Riemann limits, and the doubly periodic limits should be very easy. More precisely, I think they are boring because I believe all these limits are limits of the mixed family. but it still needs to be written down, and I intend to finish this in the near future. So the remaining thing to do is to study the saddle tower limit. This is my motivation to glue saddle towers into minimal surfaces. So Karcher Scherk saddle towers have been proved to be the only embedded singly periodic minimal surfaces of genus 0 with Scherk ends. The Scherk ends are also called wings. The picture here shows a saddle tower with 6 wings and another with 10 wings. Note that on the right side, the 10 wings form 5 pairs of parallel wings. So our goal is to glue these things into minimal surfaces. Such a glue construction is not new. Actually, Tercet first developed his node opening technique to glue saddle towers. What he did is to use saddle towers of 4 wings to desingularize an arrangement of vertical planes. The idea is to replace the vertical intersection lines by the saddle towers as we see in the picture. It was assumed that the resulting surfaces admit a horizontal reflection plane. In 2009, Rami Yunus, a student of Trecet, glued saddle towers into TPMs, but assumed again that the surfaces admit a horizontal reflection plane. In fact, we already knew many TPMs that deforms to saddle tower limits. So we see here some examples in the picture. They all admit horizontal reflection planes. But I have mentioned that the formation of the gyroid, which I recently proved, do not have reflection planes, but admit saddle tower limits, as we see in the picture here. So this suggests that the horizontal reflection planes assumed before are not necessary. So our goal in this project is to improve the glue construction by removing the assumption of horizontal symmetric plane.